Dear students, in this module we shall learn what are homotopic and heterotopic ligands, understand about the topicity and pro-stereoisomerism, study about the homotopic ligands and phases by using substitution addition and symmetry criteria. Know about enantiotopic ligands and phases by using substitution addition and symmetric criteria. Know about the diastereotopic ligands and phases by using substitution addition and symmetric criteria. Learn the nomenclature of the stereoheterotopic ligands and phases. As we know, when the atom or group of atoms in a molecule are superimposable, then they are homomorphic. These homomorphic atoms or groups can be distinguished if we are bonded to constitutionally different centers or if they have different spatial relation to the rest of the molecule. This can be clearly understood by taking an example of normal pentane as shown here in the figure. It can be seen in this case that the hydrogen atoms at the carbon atom number 2 are constitutionally heterotopic. Topos meaning place in Greek. These carbon at the second position hydrogens are stereoheterotopic as their spatial relation is different with the rest of the molecule. In this molecule, the plane methyl carbon propyl divides it into two halves, the right and the left, which are stereochemically distinguishable and enantiomorphic in the present case, actually making two hydrogens stereochemically non-equivalent. That is also called as stereoheterotopic. These hydrogens can be recognized hypothetically by replacing them with other atoms, say chlorine in this case. This results in the two enantiomers as shown in the figure 1. The replacement of either of the two hydrogens with the chlorine gives the two enantiomers. Similarly, if the replacement is by constitutionally heterotopic ligands, this would result in the constitutional isomers. For example, if methyl or propyl are replaced by the chiral groups, then it becomes diastereomorphic with respect to the plane, and chlorination at C2 leads to two diastereomers, which also make the two hydrogens stereoheterotopic. Whereas, the geminal hydrogens of the C3 cannot distinguish the two halves as it resides in ethyl carbon ethyl plane, which is two dimensionally achiral. So, the replacement of the chlorine at the C3 gives the identical products. So, these hydrogens are considered as homotopic. All these are discussed in more detail in the later sections of this module. Topicity and pro-stereoisomerism. In 1967, Mislow and Reban explained the concept of stereoheterotopicity, and in 1966, Hansen gave the concept of prochirality, which is reviewed by Eliel in 1982. Stereoheterotopicity and pro-stereoisomerism are related phenomena, as the molecules which have stereoheterotopic ligands must exhibit pro-stereoisomerism only when the ligands can be reacted on. The term chirality in pro-stereoisomerism is replaced by the term prochirality. Prochirality is defined as if two homomorphic ligands at a prochiral center or axis or a plane be made different, a chiral center or axis or a plane would result. In general, a molecule with the formula X with the ligands A, B, C represents a prochiral center. As discussed in normal pentane, which exhibits pro-stereoisomerism with C2 and C4 as pro-stereogenic centers. Like in stereoisomerism, we discuss about stereogenic elements such as centers, axes and planes. Similarly, in pro-stereoisomerism is also described in terms of analogous pro-stereogenic elements like pro-stereocenters, pro-stereoaxes and pro-stereoplanes. Also, two faces of the appropriate molecules may also be stereoheterotopic, and reactions on either phase would lead to stereoisomers. Topicity describe the relationship of two or more homomorphic ligands or phases, which together constitute a set. Hence, a ligand cannot by itself be called homotopic or heterotopic. In order to use this terminology, a comparison with other homomorphic ligand or the ligands present in the same molecule, internal comparison or in the different molecule with the external comparison is really necessary. Homotopic ligands and phases. Two criteria, namely substitution addition criterion or the symmetry criteria, are used to determine the relationship of homomorphic ligands and phases. Only one of the tests is adequate. Substitution addition criteria. Two homomorphic ligands are homotopic if substitution of first one and then the other by an atom or a group which is not already attached to the ligating center gives the identical product. For example, all hydrogen atoms in methylene dibromide, methyl bromide, ethylene and allene as represented here in the figure 2 are homotopic. Substitution of hydrogen atoms in each of these sets give a single product. The two methyl hydrogens in the plus and the minus form of dimethylethylene glycol as also in the plus and minus enantiomer are also homotopic since their respective displacement by a deuterium leads to the identical product. As shown here in the figure 3, the replacement of either of the two hydrogens gives the same product. In one case, it can be seen that the molecule 2 can be converted into the same molecule enantiomer by rotation by the angle of 180 degrees. The two faces of the double bond are homotopic if addition to either phase gives the identical product. For example, formation of ethanol by the addition of alkyl magnesium bromide to either phase of the acetone as represented in the figure 4. The two faces of dialkyl sulfide shown by the structure 4 are homotopic by the same manner. Alternatively, the two lone pairs may be considered to be homotopic. Symmetry criteria. Ligands are homotopic by internal comparison if they can interchange positions by rotation around the simple axis Cn, where n is between infinity and 1. Thus, the two hydrogen in methylene dibromide, the three hydrogens of methyl bromide and the four hydrogens of ethylene can interchange positions through rotations around C2, C3 and C2 axis as shown here in the figure 2. In allene, the geminal hydrogens are interchangeable in pairs by rotation about the molecular axis, which is the C2 axis, while the non-geminal hydrogens are interchangeable through rotation around the 2C2 axis perpendicular to the former one. All the four hydrogen atoms are thus homotopic. Similarly, for plus dimethylethylene glycol, the two methyl protons are interchangeable through rotation around the C2 axis, either in the eclipsed conformation or in the staggered conformation. This pair of ligands are therefore homotopic. The following points must be noted. Any chiral or a chiral molecule with the Cn axis, where this axis is in between infinity and 1, must contain at least one set of homotopic molecule. Molecules belonging to the non-axial point groups such as C1, Cs and Ci and also C infinity V do not possess any Cn axis, cannot have the homotopic ligands. For conformationally mobile systems, if the structural change is rapid on the time scale of observation, homomorphic ligands interchanged under the condition of fast rotation are homotopic. For example, hydrogens in cyclohexane. In a rigid molecule, the number of homotopic ligands belonging to a set cannot be greater than, although it may be equal to, its symmetry number. Faces of a double bonds, carbonium ions and molecules with di-substituted atoms capable of accepting a third ligand, for example, in the case of dialkyl sulfide, are homotopic if they interchange through the C2 axis. Stereoheterotopic ligands. The stereoheterotopic ligands are of two types: enantiotopic if their position in the molecules are related in mirror image fashion, and diastereotopic if the positions do not bear a mirror image relationship. Enantiotopic ligands and faces. Enantiotopic ligands and faces may be recognized by the application of substitution, addition and symmetry criteria. Let us look into the substitution addition criteria. Two heterotopic ligands are enantiotopic if replacement of first one and then the other by the different achiral ligand gives rise to two enantiomers. The same goes for addition to the enantiotopic faces. Some of the examples are shown here. The cases of propionaldehyde shown by the structure 5, monobromoylene, alkyl substituted paracyclophane. In all these cases, only one pair of enantiotopic hydrogens is shown. Replacement of Ha and Hb one at a time with the D, that is deuterium, leads to enantiomers. Molecules from the structure 5 to 7 provide a good example of prochiral center, a prochiral axis and a prochiral plane respectively. Addition of hydride ion to the right face of ethyl methyl ketone as shown in the figure 6 gives the enantiomer S, while addition to the left face gives the enantiomer R, that is ethyl methyl carbinol, indicating that the two faces are enantiotopic. Symmetry criteria. Heterotopic ligands or faces are enantiotopic if they are interchangeable through operation of symmetry of the second kind, that is sigma planes and the Sn axis. Thus, Ha and Hb in the structures 5, 6 and 7 in the figure 5 exchange positions through the sigma plane. These ligands are therefore enantiotopic. The enantiotopic faces of ethyl methyl ketone are likewise interchangeable through the sigma plane coinciding with the plane of the molecule. The following points should be noted in connection with the enantiotopicity of ligands. First, only achiral molecules can have internally enantiotopic ligands or faces, since the presence of a symmetry element of a second kind is necessary for an interchange. This excludes all the molecules belonging to the chiral point groups Cn and Dn and also C infinity V and C infinity H for a different reason. Molecules with enantiotopic ligands may belong to non-axial point groups, for example Ci and Cs, in contrast to the molecules containing only homotopic ligands as well as to the axial point groups. Molecules with the enantiotopic ligands and faces are not only pro-stereogenic but also prochiral. Unlike enantiomers, which occur only in the pairs, a ligand can be enantiotopic with more than one other ligand. Like enantiomers, enantiotopic ligands or faces cannot be distinguished by achiral reagents or in achiral media, but are distinguishable by chiral reagents, notably by enzymes and by NMR in the chiral media. Diastereotopic ligands and phases. Diastereotopic ligands and phases reside in diastereomeric environments and can be distinguished very often simply by an inspection of the molecular structure. However, application of the substitution addition and the symmetry criteria often makes the task easy. Substitution addition criteria. The hydrogen atoms HA and HB in chloroethene represented by the structure 8 and chlorocyclobutane represented in the structure 9 in figure 7 on substitution gives two diastereomeric products in each case and are therefore diastereotopic. Two geminal methylene protons adjacent to the chiral center are usually diastereotopic as in the molecules. The replacement criterion leads to two chiral diastereomers differing in the configuration at C2, which corresponds to erythro and trio isomers. The two faces of the carbonyl group in a molecule of a general formula as represented in the figure 8 containing a chiral center are diastereotopic, since addition of a hydride to the two faces gives different diastereomers. The structure 11 when addition takes place to the left face and the structure 13 when the addition takes place to the right face. Symmetry criteria. Diastereotopic ligands are not related by any symmetry operation and are therefore relatively easy to spot. Chiral molecules belonging to Ci point group cannot have homotopic ligands, absence of Cn, or enantiotopic ligands due to the absence of sigma and Sn, but they may contain diastereotopic ligands or faces. Frequently, homomorphic ligands at a carbon atom in chiral molecules are in diastereomeric environments and thus diastereotopic. However, this is not true in all the chiral molecules. In fact, molecules belonging to all point groups except C infinity N and D infinity V can have diastereotopic ligands. Similarly, both the chiral and the achiral molecules can have diastereotopic faces. However, such molecules must be non-planar. Enantiotopic and diastereotopic ligands often coexist. Example in the case of citric acid. Diastereotopic ligands in principle are distinguishable by all physical and chemical including biochemical means both in achiral and chiral media. NMR spectroscopy is particularly helpful in this case. Nomenclature. Symbols for stereoheterotopic ligands. Just like stereoisomers which differ in their spatial arrangements of their constituent atoms and groups, stereoheterotopic ligands also differ in their spatial relationships. So, it is desirable to give appropriate descriptors to such ligands. Configurational descriptors such as R, S, Z, E, cis and trans, which are used to describe the stereogenic units, may be prefixed with the pro and can be used to describe the heterotopic ligands attached to the analogous pro-stereogenic units. This system was introduced by Hansen in 1966. Molecules with one prochiral center. Molecules with a single prochiral center are represented by general formula C, A, B, X and X and depicted by Fisher plane projection in two perspectives A and B as shown here in the figure 9. It is assumed that the ligand A has a higher priority than the ligand B as determined by the sequence rule, while ligand X may have priority lower, higher or in between with respect to A and B. Let us assume that X has the lowest priority In order to assign a descriptor to any of the paired ligand, say XA, it is arbitrarily given a higher priority than XB, without disturbing the priorities of A and B, which are the unpaired ligands. The chirality rule is now applied to the hypothetical chiral center, which appears to have R configuration viewed from the side remote from the XB. The lowest ranking group A to B to XA describes a clockwise direction. The ligand XA is called pro-R and may be denoted by adding the subscript R as XR. The other ligand XB is pro-S denoted by XX by default. A conclusion which is alternatively arrived at by adopting the procedure but elevating the priority of XB over that of XA. By applying this Hansen procedure for assigning pro-R and pro-S symbols is to replace one of the paired ligands by a heavy isotope, that is, for example, by deuterium, and then apply the chirality rule to the now truly chiral centers. Since the heavier isotope gets over the lighter one, the assignment is the same as described. This can be clearly understood by taking an example which is depicted here in figure 10. The nomenclature of the molecule with one pro-chiral center which is allotted as R and S. Molecule with a pro-pseudo asymmetric center. The two hydrogens HA and HB at C3 of 2,4-pentane diol as shown here in the figure 11 are not homotopic. Neither they are enantiotopic, since they are not interchangeable by the symmetry of any kind, homotopic pairs of ligands. They must therefore be diastereotopic, and indeed the substitution criterion, that is replacement of HA and HB by deuterium, gives two diastereomers represented by the structure 15 and 16, in which C3 is pseudo asymmetric center with R and S configurations respectively. The carbon atom number 3 in the structure 14 may therefore be called as pro-pseudo asymmetric center, or perhaps more logically, as said by Mislow and Siegel in 1984, a pro-stereogenic center, but a pro-chitotropic center. HA is pro-R and HB is pro-S. Molecule with pro-chiral axis. Molecules like allenes, biphenyls and analogues, when suitably substituted, may have a pair of stereoheterotopic ligands. To assign descriptor to HA, its priority is elevated over that of HB. Alternatively, HA may be hypothetically replaced by deuterium. Assigning the descriptors to such molecules is to project the molecule on a plane in a similar manner as it was done for R and S. If the configuration of the hypothetical chiral axis is R, as in allene, then HA is pro-R and so on. Similar procedure is adopted for the biphenyls. Molecule with pro-chiral plane. The assignment of descriptors to heterotopic ligands in molecules with pro-chiral plane is best illustrated with an example. The substituted para-cyclophane as represented in figure 13. There are several pairs of enantiotopic hydrogens, only one pair, that is HA and B shown. They are not interchangeable by CN axis but by a sigma plane. To give a descriptor to HA, it must be given a priority over HB. Alternatively, it may be replaced by deuterium, so that the bottom methylene carbon, as underlined here, becomes the pilot atom and the hypothetical chiral plane has R configuration. So, HA is pro-R, which is represented as HR. Similarly, when HB is considered, the top methylene carbon, which is underlined, becomes a pilot atom and HB becomes pro-S, that is represented as HS. A variety of pro-stereogenic molecules contain diastereotopic ligands which on substitution gives achiral diastereomers. That is, they do not have prochiral centers or centers. Such ligands may be called as pro-Z, pro-E, pro-cis, pro-trans, pro-endo, pro-exo, etc., depending on the nature of the diastereomers formed on their substitution. Symbols for stereoheterotopic phases. Enantiotopic phases. A different system of nomenclature was given by Prelog and Hemchen in 1972 is RE and SI system, which is used to differentiate heterotopic phases. As we know, the enantiotopic phases of the molecules are two-dimensionally chiral. If the three ligands arranged in the priority order appear clockwise in a phase, the phase is RE, and if they appear anticlockwise, the phase is SI, as shown in the case of benzaldehyde in the structure 17 in figure 14. If the double bond contains two specificable trigonal atoms, a phase may be uniquely defined by two symbols, one for each specificable atom. This is illustrated with malic acid in structure 18. Here two phases are homotopic, and fumaric acid in 19, the two phases are enantiotopic. Olefins of the type 20 in which one terminal contains two equivalent ligands require, however, only one symbol Re or Si depending on the priority order of A, B and a double bonded carbon with the D2. In the figure, the priority order is A greater than B, which is greater than double bonded carbon atom. Diastereotopic phases. The two carbonyl phases of 3-hydroxybutanol as shown in the figure 15 are diastereotopic, presence of a chiral center. The right phase is Re and the left phase is Si according to the procedure to which a further subscript of R, the chiral descriptor of C3, may be added so that the double lettered subscript RER and SIR are truly diastereotopic. To summarize, homomorphic atom or groups can be distinguished if they are bonded to constitutionally different centers or if they have different spatial relation to the rest of the molecule. Prochirality is defined as if two homomorphic ligands at a prochiral center or axis or plane be made different, a chiral center or axis or plane would be result. Stereoheterotopicity and pro-stereoisomerism are related phenomena, as the molecules which have stereoheterotopic ligands must exhibit pro-stereoisomerism. Like in stereoisomerism, pro-isomerism is also described in the term of analogous pro-stereogenic elements, pro-stereo centers, pro-stereo axis and pro-stereo planes. Enantiotopic, diastereotopic and homotopic ligands can be recognized by substitution addition criteria and the symmetry criteria. Configurational descriptors such as R, S, Z, E, cis and trans, which are used to describe stereogenic units, may be prefixed with the pro and can be used to describe the heterotopic ligands attached to the analogous pro-stereogenic units. A different system of nomenclature was given by Prelog and Hemchen in 1972 is Re and Si system is used to differentiate heterotopic phases.